Hello, in this video we're going to look at how you make a free body diagram. When you're solving a problem involving forces, the first step should almost always be drawing a free body diagram. The only exception being if the problem was so simple that you could pretty much just do it in your head. But if you have more than just one or two forces, you probably want to make some kind of sketch, and this is a good systematic way to do that. So let's start with an example. Let's say that we have a boat, okay, and the boat has an engine on the back and it's sitting in the water. Alright, now there are things that are affecting this boat that are making it accelerate. One could be the boat's engine. So we've got the engine back here, and if it's on, it's going to push on the boat. We might also have a current in the water. Let's say that the current is directed up, and maybe it's windy and the wind is blowing on the boat. So those are all things that are going to act on the boat. We say that those are forces, and they have forces associated with them. There's a force from the engine, a force from the current, a force from the wind. And so together they add up to be the net force, which will tell us about the acceleration of the boat. So let's turn this sketch here into a free body diagram, which is a much more systematic way to approach the problem. And to do that, we're going to follow a recipe. Now, when you actually start solving problems, you may want to modify the recipe a little bit. Maybe you want to skip steps or combine steps. But let me just show you a very systematic way to do this, and then as you become more comfortable, you can make whatever shortcuts you want to make. The first step is to determine what the system is. The system is the object that's being described. When we say there's a net force and an acceleration and a mass, those are all for the system. So in our case, the system is going to be the boat. So we're going to represent our system now as just a dot. We don't really care what shape it has or what color it is, it's just a dot. Technically, this represents the center of mass of the object. That's more or less it's the middle. Okay, and so that's our boat. Now we normally wouldn't label it boat, that's a little excessive, but it's a representation of the boat. Okay, so let's look at our next step. There we go. Our next step is to draw all of the external forces. So in our case, we have three external forces that act on our boat. The force from the engine acts on the boat, the current acts on the boat, and the wind acts on the boat. I guess we could say that gravity pushes the boat into the water and the water pushes the boat back up. But let's just keep this into two dimensions. So we're going to ignore that direction. Technically, those are also forces. Now you might be wondering about this engine and it being external. Isn't the engine part of the boat? Yes, the engine is part of the boat, but the force is external. The force is an interaction between the propeller or the prop on the engine and the water. If you took the boat out of the water, the engine wouldn't make it move anymore. It has to be in water. That's an external thing. Okay, an internal force would be, for example, the force between the metal engine and the wooden boat, or the force between nails holding the wooden boat together. Those are inside the system, and so they can't change the system's acceleration. Only something outside of the system can change its acceleration. Alright, so imagine you're sitting in a car driving down the road. If you flap your arms while you're in the car, you can't make the car accelerate. Only things that are external to the car could make it accelerate. So that's why we wanted to define our system. Okay, so let's draw those forces on our free body diagram. Now when we draw forces on a free body diagram, we always want to put the tail of the vector where the object is and draw away from that. So for example, even though the engine is pushing on the boat, the direction of the force it causes is to the right. Okay, so we'll call that, let's call it Fe, the force from the engine. Likewise, the force from the current, we would draw like so. We'll call that Fc. And then we had the force from the wind, which we'll draw in the direction of the wind. Okay, and so those are the three forces that act on our object. Now let's look at now our next step. So we've got something set up to do a vector addition, which is what we want to do, because the next step, well, okay, maybe I'm a little bit ahead. But to do a vector addition, we need to break things up into components, and to do that we need a coordinate system. We have to choose what direction x is and what direction y is, a reference in other words. And you pick that, so choose the coordinate system. Now you choose your coordinate system typically to make the problem as easy as you can. Vectors that lie along one of the coordinates, so in this case we have one going horizontal, one going vertical, those are very easy to find the components of. So in this case we'd probably want to say that x is to the right, y is up. Okay, so that means that for the force from the engine, it's very easy to figure out what that is. It's all x component. And the force from the current, it's all y component. So once we've done that, once we've chosen our coordinate system, then we break our vectors into components so that we can add them up. So like I said, it's very easy to do for the force from the engine and the force from the current. What about the force from the wind? Well, we do have to break that one up into its components. So we would have here a negative x component and a negative y component. Let's clean that up a little bit. And we would need to have some angle theta in here. Okay, and so this x component we could say is equal to the magnitude of the wind force times cosine theta, and then this vertical component is the magnitude of the wind force times sine of theta. All right, and so now our next step. So now we have two directions. We've got the x direction and the y direction, and each direction oops, that was not the right shortcut key. That's definitely not the shortcut key. I'm trying to do a carriage return here. Let me pause. All right, and sure enough, it was the very next key I tried. So then each direction gives one equation to work with. All right, so we'll have, in this case, from the x direction, we have the net force in the x direction is equal to, well, we have the magnitude of the engine force to the right, so we'll say that's positive, and then to the left, so that must be negative based on the coordinate system I drew here, we have the magnitude of the wind force times cosine theta. Okay, and the net force from Newton's second law is equal to mass times the acceleration in that direction. We could do the same kind of thing for the y direction. The net force in the y direction is equal to the forces that are up. That would be the magnitude of the current force minus the forces that are down. So that would be the magnitude of the wind force times sine theta, and that's equal to the mass of our system times the acceleration in the y direction. All right, now supposing we knew the magnitudes of these three forces, the force from the engine, the force from the current, and the force from the wind, this would be enough information then to calculate what the acceleration was, at least if we knew the mass of the boat. All right, now there's also an optional step that I haven't written down in the recipe that sometimes you might want to do. Sometimes it's very clear that the acceleration is in a particular direction. Here it's not clear if the boat is accelerating up, down, left, right. Depends on how strong these vectors are. In other cases, it's very clear that an object is accelerating, say, down, or definitely it's accelerating to the right. In which case, sometimes you might want to represent that as sort of a hint to yourself or a reminder to yourself. We'll be doing some examples soon enough where you'll see me do that. All right, until next time.